Hello everyone, I'm Amodini. I'm a student at IIIT Sri City. I'm pursuing my BTech in computer science, and today I'll be covering a few questions on dual nature of radiation and matter. Okay, so the first question for today is, for photoelectric emission from certain metal, the cutoff frequency is V. If radiation of frequency is 2V impinges on the metal plate, the maximum possible velocity of the emitted electron will be m is the mass of the electron. So here we know that from the photoelectric equation, we know that hv dash is equal to hv plus k max. Yes, so we can write this as h into v dash is 2v, right? h2v is equal to, initially it was hv only. So hv plus half mv square. Let's make this has to be maximum, right? So I can write this further as, we've been given that v dash is equal to 2v, right? That's it. We just substitute it over here. So we can tell that hv is equal to half m v square max. And how did I get that? I just brought it over here and then subtracted it. So from here, I can tell that my v max is equal to root of 2hv by m. And this is my option B. Okay, let's move on to the next question. A source of light is placed at a distance of 50 centimeter from a photocell, and the stopping potential is found to be V naught. If the distance between the light source and the photocell is made 25 centimeter, the new stopping potential will be what? Okay, so we know that the stopping potential is independent of distance. We have learned it yesterday that the stopping potential directly depends on the frequency and not the distance, right? So since it is independent, we know that stopping potential is independent of distance. So it doesn't matter if it is kept at 50 centimeter, 25 centimeter, or even 75 centimeter. So therefore, the stopping potential will always remain V naught, and therefore our option C is the correct answer. A proton and an alpha particle are accelerated from the rest to the same energy. The de Broglie wavelengths lambda p and lambda a are in the ratio of. Okay, so we know that lambda is nothing but Planck's constant divided by momentum. Yes, so I can write this momentum to be nothing but root 2 mk, where our k is the kinetic energy. So we can say that our lambda is inversely proportional to the square root of the mass, right? So we can tell that lambda p by lambda a is equal to root of mass of alpha by mass of p. So therefore we can tell that it's nothing but 2 by 1. Why is it 2 by 1? Because this is 4 times the weight of the proton, right? So therefore, when you just square root the 4 part, you get it to be 2:1, and that is option B. Yes. Moving on to the next question. A 200-watt sodium street lamp emits yellow light of wavelength 0.6 mu m. Assuming it to be 25% efficient in converting electrical energy to the light, the number of photons of yellow light in it emits per second is. Okay. So we have been given that there's just 25% of 200 watt that is being converted, right? into the light of yellow color. So we can write this as hc by lambda into n. N is nothing but the number of photons. Here n is number of photons of yellow light. And that will be equal to 200 into 25% of it, right? So 25 by 100. Yes. So with this, I'll get my n to be 200 into 25 by 100 into lambda by hc. So substituting the values over here, we know the lambda is 0.6, and since it is micro, so I'll just multiply into 10 to the power minus 6, converting into meter basically, right? And h value is again 6.2 into 10 to the power minus 34, and c value is nothing but 3 into 10 to the power 8 meter per second. So after solving these values, you'll get 1.5 into 10 to the power 20 to be your answer. Okay, let's move on to the next question. Monochromatic radiation emitted when electron on hydrogen atom jumps from first excited to the ground state irradiates a photosensitive material. The stopping potential is measured to be 3.57 volt. The threshold frequency of the material is. Okay, so how do we do this? We have been given that from first excited state, it goes to the ground state. So n is nothing but 2 minus 1. So I can tell that my energy was 10.2 EV, and kinetic energy is nothing but the energy minus the phi, right? So I can also tell that my Q is equal to 10.2, and then the stopping potential was 3.57 minus 3.57. So Q can further be written as HV naught, and that is nothing but over here, you'll get it to be 6.63 EV, right? After calculating this. So I can further write V naught to be 6.63 into E, I'll be converting it to charge. So it's 1.6 into 10 to the power minus 19 divided by the value of h, that is the Planck's constant. And with this, you'll get your answer to be 1.6 into 10 to the power 15 hertz. So basically, you didn't really have to like calculate it hardcore because h value is somewhere 6.67, right? So, and this is over here above it's 6.63. I can approximately equate them and cancel them out. Okay. So there are a few tricks that you have to apply when you're like calculating so that you can get to the answer quickly. Okay, moving on to the next question. Two radiations of photons energies, 1 eV and 2.5 eV, successively eliminate a photosensitive metallic surface of a work function 0.5 eV. The ratio of the maximum speeds of the emitted electron is. Okay, so basically we have been given that we'll be using our Einstein's equation again. So it's nothing but K max, this will be max, right? So kinetic energy is nothing but E minus the work function, right? So I can write this as nothing but half mv1 square is equal to 1 minus 0.5 EV, right? And that's nothing but 0.5 EV. Okay, this is 1. And then again, half m v2 square is equal to, there's another one, 2.5 minus 0.5 EV. And that is nothing but 2 EV, right? So we have equation 1 and equation 2. Just divide these two. So we will get it as V1 by V2 is equal to root of, I'll cancel these halves, and then m will get cancelled, and then you'll be left with root of 0.5 by 2. Okay, so further I can write this to be nothing but 1 by root of 4. Yes, I can write 0.5 to be 1 by 2, right? I can just convert it to 1 by 2. So that will become 1 by 4. And then that is nothing but 1 by 2. So that is 1 is to 2. And our option B is the right answer. Moving on to the next question. Photoelectric emission occurs only when the incident light has more than a certain minimum power, intensity, wavelength, frequency. This is a topic that we discussed in the previous session, wherein I told about the factors that affect the photoelectric emission. And we know that for it to be minimum, it has to be our frequency, right? So basically, we know that it doesn't depend on intensity. Intensity, it doesn't depend. And then we know that there is a certain minimum thing called threshold frequency, which has to be crossed so that photoelectric emission occurs, right? So for occurrence of photoelectric effect, the incident light should have a frequency more than a certain minimum, which is called threshold frequency. Okay, so we've done this. Let's move on to the next question. The momentum of a photon of energy hv will be, okay, so we have been given the momentum, and we know that the energy is hv, and we know that I can write my p to be root 2 m e, right? But then we have our hv and c, and we know that if this is the energy, then our momentum is nothing but hv by c, right? So with this, our option A is the correct answer. Let's move on to the next question. Light of two different frequencies whose photons have energies 1 eV and 2.5 eV respectively illuminate a metallic surface whose work function is 0.5 eV successively. Ratio of maximum speeds of emitted electrons will be. Okay, this is a similar question. So we know that this kinetic energy is nothing but hv minus e, I mean the work function. So I can further write this to be half mv1 square is equal to, let's just call this 1 ev, right? So 1 minus, and then the work function is 0.5. So 1 minus 0.5, and that is nothing but 0.5 ev. Similarly, half mv2 square is equal to 1 minus 2.5, and that is, sorry, 2.5 minus 0.5, and that will be 2 ev. So we've got two things. Now what I'll do is divide the equation 1 and 2. So while dividing, half gets cancelled, m gets cancelled. So we're left with v1 square by v2 square is equal to 0.5 by 2. I can further write this as v1 by v2 is equal to root of 0.5 by 2. And therefore from here I get it to be root of 1 by 4, and that is nothing but 1 by 2, and that is our option B. Yes? Yeah. Let's move on to the next question. In photoelectric emission process, From a metal of work function 1.8 eV, the kinetic energy of most energetic electrons is 0.5 eV. The corresponding stopping potential is. Okay, so we know that the stopping potential is equal to the maximum kinetic energy, right? We know that stopping potential is equal to the maximum kinetic energy. And we have been given that the kinetic energy of the most energetic electrons is 0.5. So that means this is the Ke max. So the corresponding stopping potential. So this is the work function. We need to find the stopping potential. And we know that stopping potential is equal to the Ke max. So that will be our option C. Right? Okay. Let's move on to the next question. The threshold frequency for a photosensitive metal is 3.3 into 10 to the power 14 hertz. Yes, if the light of frequency 8.2 into 10 to the power 14 hertz is incident on this metal, the cutoff voltage for the photoelectric emission is nearly what? Okay, so we have been given that this is the threshold frequency. And then this is the incident one. And we know that the equation states that kinetic energy is equal to HV incident, let's call this I, minus HV threshold. And that is nothing but EV naught, where V naught is the cutoff voltage. Okay. So let's call this cutoff voltage. Okay. So I can write this. Now we have to find E. I'll just bring it over here. So I can write this as H by E into VI minus VTH. So subtracting the values, 8.2 VI here over here is 8.2 into 10 to the power 14 hertz. And this is 3.3 into 10 to the power 14 hertz. So substituting all the values, we'll get our V naught to be approximately equal to 2 volt. And that is our option A. So our option A is the right answer. Okay, let's move on to the next question. A source S1 is producing 10 to the power 15 photons per second of wavelength 5000 angstrom. Another source S2 is producing 1.02 into 10 to the power 15 photons per second of wavelength 5100 angstrom. Then power of S2 and power of S1 is equal to what? So basically they are asking the divided by this, right? So what I can tell is energy emitted per second by S1. I can write this to be energy emitted per second by S1. I can call this P1, okay? That is nothing but N1 into HC by lambda 1. Okay, so that is nothing but I'll further write similarly for the S2. And that is, let's call this P2. This is the energy emitted per second by the source S2. So that is nothing but N2 HC by lambda 2. Okay, so what I'll do now is we need to calculate the power, right? So I'll be like, we need to calculate it S2 by S1. So I'll put it as P2 by P1 is equal to N2 by N1 into lambda 1 by lambda 2. Why did this happen? Because it's in the denominator, right? Both of them over here, they're in the denominator. So it gets swapped and therefore you'll get that. So further, I'll write this as we have been given the lambda 1 and lambda 2, right? This is 5,000 and this is 5,100. And our N1 and N2 also have been given. That is, one is 1.02 into 10 to the power 15, and it's over here, and 10 to the power 15 is the first one. So it gets cancelled, and over here also you just multiply. So we get our ratio to be 1. So that is option A. Okay, let's move on to the next question. The potential difference that must be applied to stop the fastest photoelectrons emitted by a nickel surface having work function 5.01 eV when ultraviolet of 200 nanometer falls on it must be. Okay, so what they're telling is we need to basically find out the potential difference that must be applied to stop the fastest electrons. Okay, so fastest electrons, this is our one of the clue. So that means we are going to use ke max somewhere over here, and then we have the work function over here. Okay, so what I'll write this as, k max is equal to hc by lambda minus w, and that is nothing but hc by lambda minus 5.01. Okay, so I'll further write this as, since it's related to electron, I can use the formula directly, the angstrom one, 12375 by lambda, and it has to be in angstrom. Okay, this lambda must be in angstrom and not in nanometer. Yeah, so I can further write this to be, so since it is 200 nanometer, I'll convert it to angstrom. And how do I do that? Nanometer is nothing but 10 to the power minus 9 meter, and angstrom is 10 to the power minus 10. So I'll write this to be 12375 divided by 2000 angstrom. Yes, and minus 5.01. So I get this to be 6.1875 minus 5.01, and that is approximately 1.2 volt. So the potential difference that must be applied to stop the photoelectrons will be minus 1.2 voltage. And why is this minus? We have there are two options. There's one option which has minus and one option which doesn't. So why do we choose the minus one is because here you can see the potential difference must be acted upon so that it can stop the electrons. So for that, you apply the potential difference in the opposite direction, and therefore you have to make it negative. So therefore, with this, we got our option B to be the right answer. An electron of mass m with an initial velocity v that is equal to v naught I cap enters an electric field E is equal to minus E naught I cap. E naught is equal to constant which is greater than 0 at t is equal to 0. If lambda naught is its de Broglie wavelength initially, then its de Broglie wavelength at time t is 1. Okay, so basically we have been given few things that we have to keep in mind. So it is minus I cap, so that means it is in this direction. So I'll call this to be E naught. Okay, And then there is this electron. Yeah. And then it has a velocity v naught I cap. So it's moving in this direction, right? Yeah. And we know that the force is acting on it in the opposite direction. This is where the force is acting. So basically, what the question's telling us is we have an electron and it has an initial velocity in the direction v naught I cap. So this is my I cap. So when we write these things, right, this is I cap and this will be minus I cap, right? So therefore, v naught is in this direction. And but then the electric field is at in the direction of minus I naught. So I'll be pushing it this side. So therefore, the electron will experience a force in the opposite direction. Yes? So how do we approach this question? We know that initially lambda naught can be written as h by mv naught, right? This is the momentum. And then we also know that force is equal to mass into acceleration. And here we know that the force is E into E naught from here, right? From here, it is nothing but E into E naught. And this is the E naught acting over here. So that is equal to M into A. And from here, I can get my acceleration to be nothing but E naught by M. Yes, we got our acceleration over here. And then let's move on to the part wherein we have to talk about the final velocity, right? Our final velocity over here is going to be V is equal to V naught plus E naught by M into T. And how did I get this? Basically, we are using the Newton's law of equation. That is V is equal to U plus AT. We are just using that formula over here, right? Okay. So from here again, we also know that our final de Broglie wavelength will be h by mv, right? So I'll substitute this value in this equation. So I'll be left with h by m into v is nothing but v naught plus e naught t by m, right? So therefore, I'll get it to be nothing but I can further write this as what I'll do now is I'll take V naught out because I need, like you can see in the options, we need to bring it in the format of lambda naught. And we calculated lambda naught is equal to h. Yeah, we calculated it to be lambda naught is equal to h by mv naught, right? So therefore, we'll just remove this out and then we'll write it as 1 plus E naught by mv naught into t. So here we are adding it v naught in the denominator because it has to get cancelled to get back into the original form. So from here I can write that my lambda is equal to lambda naught by 1 plus E naught divided by mv naught into t, and that is my option A, and this is my correct answer. Okay, let's move on to the next question. The number of photon electrons emitted for light of a frequency V higher than the threshold frequency V naught is proportional to. Okay, this is one of the concept that we've learned already. And we know that the number of photon electrons that will be emitted will be proportional to the intensity of the incident light. Do not confuse it with the fact that it will be proportional to the threshold frequency. No, it will be because we are talking about the number of photon electrons, right? If we were talking about the stopping potential or anything else, then we could tell that it depends on the frequency. But we're talking about the number of photoelectrons that will be emitted, and that is directly proportional to the incident intensity of the incident light. So basically, we are telling is saturation current is directly proportional to intensity, right? Okay, let's move on to the next question. Okay, so the next question is a bit figurative. The figure shows a plot of photocurrent versus anode potential for a photosensitive surface for three different radiations. Which one of the following is the correct statement? So the statements are: curves 1 and 2 represent incident radiations for same frequency but of different intensities. 2 and 3 represent incident radiations of different frequencies and different intensities. Curves 2 and 3 represent incident radiations of same frequency having same intensity. 1 and 2 represent incident radiations of different frequencies and different intensities. So, how do we decide this? We know that the retarding potential, okay, the retarding potential depends on the initial frequency of the incident radiation. So, it depends on the frequency of incident radiation. If this was number of photons, then we could have taken the intensity into consideration, but it is about retarding potential. So therefore, we can tell that it is independent of intensity of intensity. So therefore, I can tell that my option A is the right answer. That is, curves 1 and 2 represent incident radiations, curves 1 and 2, okay, of the same frequency but of different intensities. Okay, let's move on to the next question. Monochromatic light of wavelength 667 nanometer is produced by a helium neon laser. The power emitted is 9 megawatt. The number of photons arriving per second on the average at a target irradiated by the beam is. So we have been given that lambda is equal to 667 nanometer, right? Yeah. And I can write this as 667 667 into 10 to the power minus 9 meter. So I can write my power to be 9 milliwatt, right? So that is nothing but 10 to the power minus 3 watt. Yes. So we know that our power is nothing but NHC by lambda. Yes. Where N is the number of photons emitted per second. Right. So I can write this. We need to find out N only in the end. So N is equal to P lambda by HC. So substituting all the values where P is 9 into 10 to the power minus 3. Lambda is given, that is 667 into 10 to the power minus 9. And H is 6.67 into 10 to the power minus 34. and C is 3 into 10 to the power 8. With the substituting of all these values, we'll get our N to be approximately equal to 3 into 10 to the power 16. Okay, and that is our option A. Again, we can see that there are 10 to the power 16 and 10 to the power 19 over here. Similarly, 15 and 17. And how could we arrive at these other options is by neglecting the units. So units are extremely important, like I always tell. Okay. So with this, we have covered all the questions. Now let's just go through a few concepts. Okay. So firstly, let's start with the most basic concept, that is cathode ray. Okay. So what do we know about cathode ray? Okay, so a cathode ray is an atom's stream of rapidly moving electrons. It's nothing but stream of rapidly moving electrons, right? So they can be generated at low pressures, less than 0.001 mm of a mercury column. So let's talk about the properties of cathode rays. So what is it? The first and important property of cathode ray is that the electric and magnetic fields deflect these beams. So we have the electric and the magnetic field, right? So they get deflected by these beams. Yes. Okay. And then what is the other property? The thin gold or aluminium foils are easily penetrated by cathode rays without the necessity of puncturing. And then there's also this thing wherein when they strike an object with high atomic weight, they can generate X rays. So, this is one of the use case of cathode rays. That is, when they strike an object, high atomic weight, they can generate X rays, right? So, these are like two, three important properties of cathode rays. Let's talk about the positive rays. Positive rays was basically found by Goldstein, right? So they are referred to as the gas filled in the discharge tubes moving positive ions. So here also positive rays also, the thing is that in both electric and magnetic field these rays are deflected. Only a straight path will allow these rays to travel. The cathode rays travel at a faster speed than the positive rays. Okay, this is one of the things that you have to remember. So let's talk about Hertz observation. Okay, so this is an off topic, and that is Hertz observations. Okay, so basically, Heinrich Hertz made the discovery of photoelectric emission. Okay, so while conducting this research on electromagnetic waves, he noticed that when light passes through a metal detector, let's call this metal detector loop. Okay, this is a loop, let's just call it. So, when light passes through this metal detector loop, the electrons on the surface gain enough energy to displace the positive ions attraction force and exit to the surrounding area. Okay, so on this surface, okay, there would have been many electrons, right? So whenever the light passes, these electrons get enough energy, okay, such that they displace the positive ions. Okay, and therefore they exit into the surrounding area. Okay, let's talk about the other observations. Basically, the experimental setup of this photoelectric effect consisted of a metal plate. Okay, it consisted of a metal plate that's basically a collector. And then a photosensitive plate that is nothing but an emitter. It was attached to a quartz tube. Okay, so basically, what they found out is in the absence of air resistance, this tube will permit electrons to go through the emitter to the collector. So basically, emitter is here and then the collector is here. And due to the absence of air resistance, it will permit the electrons to go from the emitter to the collector. Okay. The potential difference between the two plates is sustained by the battery. We are using a battery over here. Right. So the commutator has the ability to reverse the polarity. Right. So with this, we'll get a graph that they observed. And this is one of the important graphs that we must understand. So this is the retarding potential over here, and this is the anode potential. And from here, our graphs go like this: 1, 2, and third one. Okay. And this particular point is nothing but stopping potential. These rays which are there, these are actually of different intensities basically. This is I1, this is I2, and this is I3, right? So electrons are released and visible light is absorbed by the photosensitive plate. That is nothing but the emitter, right? So a photoelectric current flows from emitter to collector. Therefore, this is consistently in the opposite direction, right? So from this, basically, it gave rise to the next equation that we'll be learning. That is nothing but Einstein's photoelectric equation. And we have learned it already, and that is nothing but E is equal to H V minus phi, right? So basically, here we'll be talking about particle nature of light and the wave nature of light, right? So the photoelectric effect provides proof that light behaves as quanta or energy packets with an H value when it interacts with the matter. Okay. So this is like one of the concepts that we have to like remember. That is the whole topic about when we talk about this dual nature of radiation is the particle nature and the wave nature. And in the particle nature, basically these electrons act as this energy packets or quanta. So when they are in the particle nature, and during the wave nature, they exhibit wave-like properties, right? It has momentum and everything. So let's have a recap of everything we did till now. So, firstly, we started solving questions, and today the major questions were revolving around this equation itself, right? So, this is the one of the major equation, and there were questions that revolved around de Broglie wavelength too. And what does that indicate? That in this chapter, there is more focus given to the Einstein's equation and the de Broglie wavelength. So you can explore more questions when it comes to these topics. And then we discussed about cathode rays, positive rays, and how the Hertz observations and the photoelectric setup, right? So, why is the photoelectric setup important? Because there might be theoretical questions that might just arise about the emitter or the collector, from where the photoelectric current is passing, the direction of the photoelectric current. These questions could arise. And why did we talk about the Hertz observations? Hertz observation was the spark for the photoelectric effect, right? So, it was one of the beginning for the photoelectric emission, right? So therefore that is important. And after that, the other thing that is important is the particle nature and the wave-like nature. And over here we have studied about the Davison Germer experiment, right? So in that experiment, what did he do? It has been verified using the nickel crystal, right? So we could see that there were diffraction angles and everything whenever the electrons approach the nickel, right? So this was one of the thing that we learned. So right now, what is your responsibility to do is to go back, revise these concepts, all these concepts, be it theoretical or the ones based on formula, and then come back and solve all of these questions on your own. And if you get stuck, then you have to go through the video and then learn, and then just don't limit yourself to these questions itself. Go ahead and explore more. If then, as in there was a question on Einstein's equation, then just don't stop on Einstein's equation. Try and calculate the de Broglie wavelength, try and calculate the kinetic energy, try and calculate the stopping potential. So these are a few terms that you have to know what it means and when. And the most important rule is that photoelectric emission does not happen until and unless it is greater than threshold frequency, right? Threshold frequency is the certain minimum frequency that has to be passed so that an emission happens. So these are the few pointers that you have to remember. And as always, like I always tell you guys, make sure to not mess up with the units, because it's really important. And when it comes to these high calculation questions, there are chances that it could be given in nanometer and you end up calculating it in angstrom, and then such silly mistakes just deprive you of those 4 marks, and then it would also give you a negative marking. So to avoid that, make sure that you check the units and then convert it to all base units and then solve it, right? And when it comes to solving, like when we talk about heavy calculations, if the options are not closer to each other, then make sure that you can approximate the values and then cut it down. Let's just say I have 4.268 and I have 2.211. Okay, so I can approximate this to be approximately 2, right? And my option that has 2 in it, I can just correct it to be the right answer. If the options are near like 2.1, yeah, 1.99 or something like that, don't take this risk. Make sure that you calculate it completely. Okay, so with this, I hope you keep all these tips on in your mind, and then make sure to practice, because until and unless you don't practice, you won't be able to ace it. So practice is what you have to do, and just put in all your efforts, and then you'll be able to ace it. So that's it for today. Thank you so much, everyone.